Imagine standing alone on a perfectly still night. No city lights, no noise, just you, the wind, and the stars, countless, cold, and ancient, staring back from the velvet dark. You look up, and suddenly it hits you. Where does it all end? Is the universe like an endless ocean, stretching forever in every direction? Or is it more like the surface of a globe, finite but with no edge, looping back on itself so that if you traveled far enough, you'd return to where you began, only to find your own back staring into the distance? This isn't philosophy. This is physics. And for over a century, scientists have been chasing an answer to one of the most haunting questions in existence: what is the shape of the universe? Not its contents, stars, galaxies, black holes, but its very geometry, the scaffold upon which everything is built. The silent architecture of reality itself. We've mapped the human genome. We've touched the edge of black holes with radio telescopes. We've watched space-time ripple from collisions billions of light years away. Yet this, whether space is infinite or wraps around like a cosmic video game screen, remains one of the deepest unsolved puzzles in cosmology. And here's the twist. The answer might already be hiding in plain sight, encoded in the faint afterglow of the Big Bang, if only we know how to read it. But before we decode that whisper from the dawn of time, we need to understand something far more basic, something even Einstein grappled with. How do you measure the shape of everything when you're stuck inside it? Think about how you'd figure out the shape of Earth if you'd never seen it from space. You couldn't just step outside and look. You'd have to infer it from what you can. See, like how ships disappear hull first over the horizon, or how shadows change length at different latitudes. That's exactly the problem cosmologists face. We are trapped inside the universe, like ants on a balloon, trying to guess whether the surface curves, stretches flat, or folds in on itself. But here's where it gets brilliant. We don't need to leave the cosmos to measure its shape. We just need a ruler, and nature gave us one. In the early universe, sound waves rippled through the hot, dense plasma-like vibrations in a drum. When the universe cooled enough to become transparent, about 380,000 years after the Big Bang, those waves froze in place. They left behind patterns, hot and cold spots in the oldest light we can see, the cosmic microwave background. These frozen ripples are our cosmic yardstick. They have a known physical size, about 500 million light-years across, based on how fast sound could travel in that primordial soup. So when we look at the sky today and measure the apparent size of those spots, we're doing something extraordinary. We're using geometry to probe the curvature of space itself. If space were positively curved, like the surface of a sphere, those spots would appear larger than expected because light rays would converge as they traveled toward us. If space were negatively curved, like a saddle, they'd look smaller as light rays diverge. And if space is flat, they'd appear exactly the size physics predicts. It's the same principle surveyors use on Earth, just scaled up to the entire observable universe. This isn't guesswork, it's precision cosmology. And the results? They've stunned scientists and reshaped our understanding of reality itself. For centuries, we assumed space was just empty, a static stage where matter moved, but nothing more. Then Einstein showed us space isn't passive, it's dynamic, bendable, woven together with time into a single fabric, space-time. And, like any fabric, it can curve. But not just near stars or black holes. The entire universe could carry a global curvature, subtle but all-encompassing. Cosmologists describe this curvature in three possible ways. First, flat. Not flat like a piece of paper in 3 dimensions, but flat in the geometric sense. parallel lines stay parallel forever. Triangles have angles that add up to exactly 180 degrees. And space extends as far as the math allows without looping or flaring. Second, closed. Imagine the surface of a sphere, but in 3 dimensions. No edges, no center, but finite. Travel far enough in one direction, and you'd circle back to your start. In this universe, parallel lines eventually meet. Triangle angles sum to more than 180 degrees. And gravity, over cosmic scales, would be strong enough to one day reverse the expansion, pulling everything back in a big crunch. Third, open. Here, space curves away from itself like an endless saddle stretching in every direction. Parallel lines diverge. Triangle angles fall short of 180. And expansion wins forever. Galaxies racing apart until the cosmos fades into cold, eternal silence. These aren't just abstract ideas. They're predictions rooted in Einstein's equations and in the amount of matter and energy the universe contains. Too much mass, and gravity closes the cosmos. Too little, and it flies open. Just the right amount, and space balances on a knife's edge, perfectly flat. So, which one is ours? The answer, as it turns out, is written in the oldest light in existence. In the year 1965, 2 radio astronomers in New Jersey stumbled upon a faint, persistent hiss coming from every direction in the sky. At first, they thought it was pigeon droppings messing with their antenna, but it wasn't noise. It was the afterglow of creation itself, the cosmic microwave background, or CMB. The moment the universe became transparent, releasing its first light, now stretched by cosmic expansion into microwaves, cold and ghostly. Decades later, satellites like COB, WMAP and Planck mapped this glow with astonishing precision. They didn't just see a smooth sea of radiation, they saw ripples. Tiny temperature variations, 1 part in 100,000, like fingerprints left by the infant universe. And among those ripples were the frozen sound waves we talked about, the standard rulers of cosmology. When scientists measured the angular size of those ripples in the sky, something remarkable emerged. The spots were exactly the size expected in a flat universe. Not slightly larger, not slightly smaller. Within the margin of error of our best instruments, space shows no detectable curvature on the largest scales we can observe. This result didn't just settle a debate, it reshaped physics. A flat universe implies something astonishing. The total energy density of the cosmos is precisely balanced at the critical density. But here's the catch. Ordinary matter, the stuff of stars and planets, makes up only about 5% of that. Dark matter adds another 25%. The rest, a mysterious force now called dark energy, pushing space apart with relentless acceleration. So the data says, on observable scales, the universe is flat. But, and this is crucial, flat doesn't automatically mean infinite. It could still be finite yet flat if it has a non-trivial topology, like a video game screen that wraps around. Which brings us to a haunting possibility. What if the universe is looping, and we've just never seen the evidence? Picture this. You're in a room with mirrored walls. Look one way and you see yourself. Look another, and there's another copy. Then another, fading into infinity. Now imagine the entire cosmos is like that room, but in 3 dimensions. If the universe is finite and loops back on itself, what cosmologists call a multiply-connected topology, then light from a single galaxy could reach us from multiple directions, like echoes bouncing through a hall of cosmic mirrors. In such a universe, we wouldn't just see one version of the Andromeda galaxy. We might see it again, older, fainter, coming from the opposite side of the sky, because its light took a longer path, wrapping all the way around space before arriving at our telescopes. These would be ghost galaxies, duplicates of real objects, displaced in time and direction, but unmistakably the same. Scientists have hunted for these echoes. They've scoured the CMB for matching circles, pairs of identical temperature patterns on opposite sides of the sky that would signal space wrapping around like a torus or a dodecahedron. They've compared galaxy catalogs, searching for repeating structures. So far, nothing conclusive. No ghost galaxies, no matched circles, no sign of cosmic mirroring. That doesn't rule out a looping universe. It just means if it does loop, the loop is larger than the observable universe itself. Think of an ant on a very large balloon. From its tiny viewpoint, the surface looks flat and endless. Only if the balloon were small enough would the ant notice it's walking in circles. We may be in the same situation, trapped in a patch of space so vast that any curvature or repetition lies forever beyond our horizon. And that horizon is real. Light has only had 13.8 billion years to travel. So even if the universe is finite and looping, we might never see the seam because it's simply too far away for light to have crossed it yet. The cosmos could be a hall of mirrors, and we're standing too close to the wall to notice. There's a cruel irony at the heart of cosmology. The universe gives us clues, but it also sets hard limits on what we can ever know. The observable universe. The sphere of space from which light has had time to reach us is finite. About 93 billion light-years across, thanks to the expansion of space itself. But beyond that, darkness. Not just empty space, but unknowable space. A boundary not of distance, but of causality. Even if the universe is finite and loops back on itself, if that loop is larger than our cosmic horizon, we'll never see it. It's not a technological limitation, it's a law of physics. No signal, no light, no information can cross that divide. We are forever confined to our cosmic patch-like sailors on a fog-bound sea, unable to see whether the ocean ends or circles back to shore. And here's another twist: cosmic inflation. The theory that the universe underwent a burst of exponential expansion in its first fraction of a second suggests that the entire universe could be unimaginably larger than what we see. Some models say it's at least 10 to the power of 23 times bigger than our observable bubble. In that vastness, our flat, smooth patch might just be a tiny, unremarkable region in a much wilder whole. Perhaps with different geometries, even different physics in other domains. So when we say the universe is flat, what we really mean is the part we can see is flat. That's honest science. But it's also humbling. We may never know the true global shape, whether it's infinite, finite but unbounded, or something stranger still. The answer could be written in regions of space-time forever sealed off from us by the speed of light and the relentless stretch of expansion. And yet, that uncertainty isn't a failure. It's a reminder. We're not outside the universe looking in. We're of its stardust, trying to understand the shape of its own cradle. And sometimes, the most profound discoveries aren't answers, but the courage to live with the questions. We live in a time unlike any other. For most of human history, the shape of the world was myth-flat Earths, turtlebacks, celestial spheres. Now, we've measured the curvature of space-time itself with satellites colder than deep space and telescopes that see back to the universe's first breath. And still, the ultimate shape of everything remains just out of reach. But maybe that's not a flaw in our knowledge. It's a feature of existence. The universe doesn't owe us a neat answer. It doesn't have to be infinite or finite in a way we can easily picture. It only has to be, and in that being, it invites us not to certainty, but to wonder. Think about what it means to stand under the night sky, knowing that every photon hitting your eye has traveled for millions, even billions of years, across a geometry we're still trying to fathom, just to meet you here, now. You are not separate from this mystery. You are woven into it. Your atoms were forged in stars that exploded in a space whose shape we can't fully grasp. Your thoughts are patterns of electricity dancing in a brain that evolved under a sky full of unanswered questions. And that's beautiful, because the search for the universe's shape isn't really about maps or math. It's about our place within the whole, whether space loops or stretches forever, whether it's one bubble in a multiverse or the only stage that ever was. What matters is that we're here, asking, reaching, listening to the faint echo of creation and daring to interpret its song. So the next time you look up and feel small, remember, you're not just in the universe, you're part of its self-awareness. And as long as we keep wondering about its shape, its fate, its silence, we keep the oldest human story alive, the story of curiosity, written in starlight and space-time.